Hi everybody. Last week, we talked about hypothesis testing with proportions. This week, we're going to talk about how we deal with hypothesis testing when we have means instead of proportions. Last week, we were able to utilize the central limit theorem because just by knowing the population proportion, we are also able to calculate the population standard deviation. This isn't true in general, but let's start with an example where both the population mean and standard deviation are known. When we have easy access to the population, it's often possible to know the standard deviation of the population. So one example of that is with standardized tests. So let's suppose that we want to determine if students in Dr. Edge's statistics class do better than the average Denison student on the ACT. Suppose it is known that the average ACT score on Denison's campus is a 29.5 with a standard deviation of 2.5, and that the 68 students in Dr. Edge's class scored a 31 on the ACT on average. So we want to know if there's strong evidence to suggest that Dr. Edge's students do better than average on the ACT. Recall that the central limit theorem tells us that the average ACT score is going to be normally distributed with mean 31 and sigma equal to 2.5 divided by the square root of 68, as long as the sample size is sufficiently large. For means, we say that there is a sufficiently large sample if we have at least 30 observations. So in our case, we have a sufficiently large sample. So our hypotheses for these experiments are, well, our null hypothesis is that the mean is exactly the same, or 29.5, and our alternative hypothesis is that the students in our class do better than the average Denison student, or that the mean is greater than 29.5. Just like before, we can calculate the probability of something as extreme or more extreme than our observed sample of 31 occurring by using R. And whenever we talk about the observed mean, we usually use the letter X with a bar over the top of it. So we can input mu, sigma in, we can calculate the standard deviation, and we can calculate X bar, and we put all of that into R, and then we use the p-norm function to calculate the probability. In this case, notice that we get 3.75 times 10 to the negative 7th. That E, again, means times 10 to the whatever power follows it. So this is not a large number, this is a very small number. Essentially, we need to add 6 zeros in front of the 3 to get the very small decimal of our p-value. Thus, because our p-value was so small, we can reject the null hypothesis and say that there is strong evidence to suggest that students in Dr. Edge's class did better than the average Denison student on the ACT. Again, in general, when we're calculating a p-value, we always assume that the null hypothesis is true. Namely, this usually means that we assume that the mean is some value. In order to be able to apply the central limit theorem, we also need to know the population standard deviation sigma. When we are calculating the p-values for proportions, though, we could always calculate sigma because sigma was just based on p. In general, though, from a random distribution, we're not going to have access to or be able to calculate the population standard deviation because, as I've said a million times, it is often impractical or impossible to find that information from a population. There are two scenarios in which we will not be able to apply the central limit theorem. The first, and the usual one, is that we don't have access to the population standard deviation sigma. The second is that our sample size is not sufficiently large. So what do we do in either of these cases? Well, it turns out that there's another distribution called a t-distribution that we're going to be able to use instead. So before we talk about the details of the t-distribution, let's go back in time and look at the history of the t-distribution. So the t-distribution is also called student's t-distribution, and it was discovered in the mid-19th century by a man named William Seeley Gossett, who worked at Guinness. So he was trying to determine the quality of some small batches of beer that he was brewing. But because he was working with really small sample size, he couldn't utilize any of the then quite modern statistical methods. That is, he wasn't able to apply the central limit theorem to his hypothesis testing because he didn't have a sufficiently large sample to do so. So he went ahead and developed a new distribution that would allow him to test the small samples, which was called student's t-distribution. And it was called students' t-distribution because Guinness didn't want to tip off its competitors by letting them know they were using a new statistical method to check the quality of their beer. And so Gossett published his work under the pseudonym of Student. So what does the t-distribution look like? First, it's important to note that when we say the t-distribution, we're actually talking about a family of distributions which depends on how large the sample size is. The t-distribution, though, always has mean of 0 and a standard deviation of n minus 1 divided by n minus 3, where n is the sample size that we're working with. So you can see here the picture where n is equal to 3, 5, 20, and 30, and finally we see the z, which is the standard normal distribution. So as the sample size gets arbitrarily large, the t-distribution approaches the normal distribution. A term you'll often see associated with the t-distribution is what is called degrees of freedom, or df. In essence, degrees of freedom is just the size of our data minus the number of calculations or estimations we have to make from that data. In our case, because we don't know the population standard deviation, we estimate it from our sample, and thus we lose 1 degree of freedom from our sample. So for the t-distribution, the degrees of freedom is just the sample size minus 1. As I mentioned before, the mean of a t-distribution is always 0. So unlike with the normal distribution, we are not going to be able to change the mean and standard deviation of the t-distribution to whatever we want. So before we can calculate a probability with the t-distribution, we have to calculate a so-called t-score, which has the following formula. It's just x bar minus mu divided by s over the square root of n, where x bar is our sample mean, mu is the assumed mean in our null hypothesis, s is the sample standard deviation because we don't have access to the population standard deviation, and n is the sample size. If you remember back to a z-score, a t-score is just the analogous thing for a t-distribution that a z-score is for the standard normal distribution. Now, let's see how we use a t-distribution when we conduct a hypothesis test on a single mean. Suppose that a study of 24 Denison students shows that Denison students study on average 20.1 hours per week with a standard deviation of 1.3 hours. A consultant hired by the university suggests that students should be studying at least 21 hours per week. We want to know, is there a significant difference between how much Denison students in the poll studied versus the consultant's recommendations? Our hypotheses in this case are, the null hypothesis, or the status quo, is that Denison students study the same as the consultant's recommendation of 21 hours, and our alternative hypothesis is that they study differently than 21 hours. So our null hypothesis is that mu is 21, and our alternative hypothesis is that mu is not 21. So in this case, the first question you should always ask yourself, can we calculate a p-value using a normal distribution? No, in this case we can't because the sample size is too small. Also, we don't know what the population standard deviation is. And so we will have to use a t-distribution with 23 degrees of freedom, because the degrees of freedom for the t-distribution is just the sample size minus 1. So first, we need to calculate a t-score before we can calculate a probability from the t-distribution, which can be done in R. So again, our sample size is 24, our assumed mean is 21, our observed mean is 20.1, our observed sample standard deviation is 1.3, and so using all of that information, we plug it into our t-score to get that t is equal to negative 3.39. We can now use that t-score to calculate the probability of something being different than 21 hours. And so, like before, we are using the p-norm function. This time we're going to use the pt function, which we'll discuss more in our activity in class later this week. And remember, since this is a two-sided test and the t-distribution, like the normal distribution, is symmetric, we're able to just calculate one side of the probability and then multiply that number by 2. Thus, when we do that, we see that we get a p-value of 0.031. And because this value is less than 0.05, we will say that we have enough evidence to reject the null hypothesis in favor of the alternative hypothesis, or that the amount Denison students study is significantly different than 21 hours. In our next lecture, we'll talk about how to deal with hypothesis testing when we have a difference of two means.